Hi, good morning once again. ഇന്ന് നമ്മളൊരു മോളിക്കുലാർ സിമ്മട്രി ആൻഡ് എന്താ പറയുക ഗ്രൂപ്പ് തിയറി എന്ന് പറയുന്ന ചാപ്റ്റർ നമുക്കിവിടെ ക്ലോസ് ചെയ്തു. അടുത്ത ഒരു ചാപ്റ്റർ ഒരു വലിയ ചാപ്റ്ററാണ് കാർബോക്സിലിക് ആസിഡ്സ് ആൻഡ് സൾഫോണിക് ആസിഡ്സ്. അത് പണ്ട് സിലബസിൽ 18 അവറായിരുന്നു. ഇപ്പോൾ അത് അവർ കുറച്ചിട്ടുണ്ട്, 12 അവർ എന്ന പേര്. പക്ഷെ എന്നാലും 10-16 അവർ പഠിപ്പിക്കണം, അത്ര അധികം ഉണ്ട് പഠിപ്പിക്കാനായിട്ട് എല്ലാവരും. അപ്പോൾ അതും ഈ സ്ലൈഡുകൾ വഴി ഓർഗാനിക് കെമിസ്ട്രി പഠിപ്പിക്കാൻ സ്വല്പം ബുദ്ധിമുട്ടാണ്. അതിൻ്റെ സ്ലൈഡുകൾ ഉണ്ടാക്കാൻ നല്ല സമയം പിടിക്കും. പറ്റായല്ല, സമയം നല്ല ഭംഗിയായിട്ടുള്ള സ്ലൈഡുകളൊക്കെ ഉണ്ടാക്കാൻ പറ്റും. ബീമർ എന്ന് പറയുന്ന സ്ലൈഡുകളാണ് ഞാൻ മാഷ് ഉപയോഗിക്കുന്നത്. ലാറ്റക് എന്ന് പറയുന്ന പ്രോഗ്രാം ഉപയോഗിച്ചുകൊണ്ടുള്ളതാണ്. അപ്പം അതിലിതെല്ലാം ചെയ്യാൻ പറ്റും, പക്ഷെ സമയം എടുക്കും. അതാണ് ഇതിലെ പ്രശ്നം. അതുകൊണ്ട് നമുക്കൊരു 15-20 മിനിറ്റ് ക്ലാസ് ഒരു ദിവസം ഉണ്ടാവുള്ളൂ. പക്ഷെ അതുകൊണ്ട് കുറച്ചധികം കാര്യങ്ങൾ കവർ ചെയ്യാൻ പറ്റും ചെയ്യും. എന്നാൽ നമുക്ക് തുടങ്ങാമെന്ന് എനിക്ക് തോന്നുന്നു. ആദ്യം തന്നെ നമുക്കതിൻ്റെ സിലബസ് നോക്കാം. സിലബസ് കാണുമ്പോൾ നിങ്ങൾക്ക് മനസ്സിലാവും. കാർബോക്സിലിക് ആസിഡ്സ് ആൻഡ് സൾഫോണിക് ആസിഡ്സ്. അതിൻ്റെ സിലബസ് എന്ന് ഞാൻ പറഞ്ഞല്ലോ. സിലബസ് ഒന്ന് നോക്കിക്കോളൂ. Carboxylic acids, nomenclature, isomerism, preparation, hydrolysis of nitrile and carboxylation of Grignard reagent, chemical properties. Acidity, effect of substitution on the acidity of aliphatic and aromatic carboxylic acids, HVZ reaction, decarboxylation, called by electrolysis, mechanism expected, action of heat on dicarboxylic acids, Planck's rule. Preparation, reactions and the uses of carboxylic acid, cinnamic acid and citric acid, role of lactic acid in exercise, preparation and reactions of acid derivatives, acid chlorides, esters, amides and acid anhydrides, comparison of boiling point and reactivity of acid anhydrides, comparison of boiling point and reactivity of acid derivatives, ascending and descending carboxylic acid series, sulfonic acid, preparation and properties of benzene sulfonic acid, tosylation, synthesis and application of saccharin, comparison of acidity of alcohols, phenols, carboxylic acids and sulfonic acids. ഇത്രയാണ് നമ്മുടെ സിലബസിലുള്ളത്. ഒരു ഐഡിയ കിട്ടിക്കാണെന്ന് വിചാരിക്കണം. Okay, then let me come to the topic. What are carboxylic acids? Carboxylic acids are nothing but organic compounds containing the functional group COOH. It is shown in this way, are called carboxylic acids. It's well familiar. Example, see, this is the carboxylate group and this is an alkyl chain to which carboxylic acid group is attached. So it forms a carboxylic acid. Since the alkyl group is aliphatic in nature, it is known as aliphatic carboxylic acid. See, this is the carboxylic acid group or carboxylate group. It is attached to an aromatic system, so it's an aromatic acid. This one is benzoic acid. Then next aspect regarding organic acids, carboxylic acids, is a classification. There are several types of classification. Out of these we have to see 2 or 3 types. First one is classification based on aromaticity. See, this one is not aromatic but aliphatic. This is an example for aliphatic carboxylic acid and the compound is methanoic acid. Why it is so? In the naming നമ്മൾ അടുത്ത സെക്ഷനിൽ പറയും. nomenclature, IUPAC nomenclature and trivial nomenclature. This one is this compound is a carboxylic acid since it contains a carboxylate group and the attached group, the group attached to this carboxylate group, that is aliphatic in nature, hence it is an aliphatic carboxylic acid. See, this one is an aromatic ring attached to this carboxylic acid group, so it is aromatic carboxylic acid. This one is benzoic acid. Exact compound is a benzoic acid, actual name. This one, you compare this one, similar to this benzoic acid, but no double bonds are there. It's a cyclohexane ring attached to this carboxylic acid group, hence cyclohexanoic acid. And this one is an alicyclic group, hence alicyclic type carboxylic acid. Good idea. So first classification based on aromaticity is over. Then classification based on number of carboxyl groups. Depending upon the number of carboxylic groups attached to a hydrocarbon chain, it can be classified into monocarboxylic acid, dicarboxylic acid, tricarboxylic acid, etc. See, this one, ethanoic acid, or simply known as acetic acid. This acetic acid contains only one carboxylic acid group, hence it is of the category monocarboxylic acid. And see, oxalic acid. This one is oxalic acid. Oxalic acid contains two carboxylate group, hence it is known as dicarboxylic acid, dicarboxylic acid. And you consider this compound. See, it's an aromatic ring, benzene ring, to which alternate positions of this compound COH group is attached. See, 3 COH groups are attached to alternate positions of the benzene ring. Okay, so according to IUPAC, we can name in this way 1,3,5 benzene trioic acid. It's an example for tricarboxylic acid. Why it is known as tricarboxylic acid? 3 carboxylic acid groups are there. See, it's a cyclohexane ring to which opposite positions, it's usually known as para positions or 1,4 position. To the 1,4 position, COH group is attached. Cyclohexane dioic acid. And positions may also be given. Actually, I have not shown the positions. Whenever you include the positions, how can you number, how can you name this compound? 1, 2, 3, 4. 1,4 cyclohexane dioic acid or cyclohexane 1,4 dioic acid. Both are same. Since it is contains 2 carboxylic acid groups, it is known as dicarboxylic acid. And based on this way, depending upon the number of carboxyl groups, all hydrocarbons can be, not hydrocarbons, carboxylic acid can be classified into monocarboxylic acid, dicarboxylic acid, tricarboxylic acid, and so on. So that's always the classification based on number of carboxyl groups. Next one is classification based on the basis of saturation. You know what is meant by saturated organic compound and unsaturated organic compound. You know better. Anyway, I am not going to much details. See, the first example is ethanoic acid. Carboxylic acid. This is a carboxylic acid group attached to a saturated hydrocarbon chain. Ethanoic acid. So this carboxylic acid is a saturated carboxylic acid. Whereas you consider crotonic acid, crotonaldehyde, crotonic acid, well familiar to you. See, it's a carboxylic acid group attached to an unsaturated chain. Hence it is an example for unsaturated carboxylic acid. You consider cinnamic acid. This is a cinnamic acid. C6H5 or a phenyl ring attached to this crotonic acid group. CH double bond CH-COH. Here also carboxylic acid group attached to an unsaturated system. Why benzoic acid is not considered as an unsaturated carboxylic acid? This ring is not considered as unsaturation because it is resonance stabilized. It's almost stable as that of a saturated chain. Hence it is so. Anyway, see, this one is a cyclohexane dioic acid. Cyclohexane dioic acid. 1,4 cyclohexane dioic acid. What about this classification? On the basis of saturation, it is a saturated one. Out of this, 1, 2, 3, 4 carboxylic acid given in this slide. 2 are unsaturated and 2 are saturated. Which are they? The unsaturated ones are, see, this one as well as this one. Got the idea? Anyway, I'm not going to much details. Then nomenclature. What is meant by nomenclature? Naming of organic compounds. And next aspect regarding carboxylic acid is the nomenclature of carboxylic acid. Let me come across this aspect. Trivial names are related to the source of the acid. Source means from where that acid is obtained. For example, formic acid is a well-known example. Formica is the Latin term used for the red ant, and formic acid is first isolated from these red ants, hence the name formic. Formic acid, the term formic acid comes from formica, which means red ant in Latin. Okay, what I mean is this: trivial names are related to the source of the acid. IUPAC names are formed by combining prefixes, if any. This prefix stands for substituents or certain groups which are indicated by prefixes, plus word root, plus primary suffix, plus secondary suffix, oic acid. In the previous semesters, you might have seen naming of organic compounds. An organic compound, name of an organic compound consists of the word root. Good idea. And where from that word root comes, so depending upon the number of carbon atoms in the longest chain. Okay. Then primary suffix. Primary suffix is depending upon the type of saturation or unsaturation. ANE for saturated compounds. If it is an alkyne group or alkyne branch, alkane, ANE, alkane. Then primary suffix is ene. Sorry, I have made a mistake. If it is alkane, ANE, the suffix ANE. If it is alkene chain, the primary suffix is ENE. If it is alkyne branch, primary suffix is YNE. Along with the functional group is indicated by the secondary suffix. For example, in the case of carboxylic acid, the secondary suffix is used is oic acid. In the case of alcohol, it is known as ol. In the case of aldehyde, Al. All these things. And depending upon the branching, number of branching or the position of branching, these are indicated by the prefixes. Sometimes there may not be any prefixes also. You got the idea? Okay, let me go to some examples. HCOH. This one is formic acid. IUPAC name. This contains only one carbon atom, hence the word root is METH, meth. And since it is saturated, the primary suffix is ANE, hence methane. Methane, basic structure is methane. Then secondary suffix is oic acid. No prefixes are there since there are no substituents. So the IUPAC name is methanoic acid. It obtained from word root meth plus primary suffix ANE, then secondary suffix oic acid. Okay, formic acid, methanoic acid. Then the second one, CH3COH. It is known as acetic acid. Why it is so? I already told you. Trivial names are come from the source from which they are obtained. And acetic acid is usually isolated from, in the previous days, isolated from those compounds which are citrus. നമ്മൾ മലയാളത്തിൽ പുളിരുചിയുള്ള എന്ന് പറയും. വിനെഗറൊക്കെ നിങ്ങൾക്ക് പരിചയമുണ്ട്. വിനെഗർ അല്ലേ? തൃശ്ശൂർ അതിനെ ചൊറുക്ക എന്നൊക്കെ വിളിക്കുന്നത്. ചൊറുക്ക. വിനാഗിരി എന്നാണ് അതിൻ്റെ മലയാളം, ശരിയായിട്ടുള്ള മലയാളം. വിനാഗിരിയിൽ അല്ലെങ്കിൽ അതുപോലെ പുളിരസമുള്ള സാധനങ്ങളിലൊക്കെ ഉള്ള ഒരു ആസിഡാണ് അസറ്റിക് ആസിഡ്. അസറ്റം എന്ന് പറയുന്ന സിട്രസ് എന്നർത്ഥം, പുളിരുചിയുള്ള എന്നർത്ഥം. അങ്ങനെയാണ് അസറ്റിക് ആസിഡ് പേര് വന്നത്. CH3COH is known as, trivially it is known as acetic acid. According to IUPAC, word root corresponding to this compound is ETH. Why it is so? It corresponds to two carbon atoms. Word root ETH, since it is saturated, the primary suffix is ANE, then secondary suffix corresponding to the functional group is oic acid, hence ethanoic acid. Then you compare the third one. Here the word root is 1, 2, 3, 4. Okay, got the idea? Word root is bute. Okay. Then primary suffix is ane since it is saturated, and the secondary suffix corresponding functional group is oic acid. No prefix are there. So you combine word root, primary suffix, secondary suffix. Bute plus ane plus oic acid, butanoic acid. This is the IUPAC's name. Somewhat simple. And the trivial name, it is known as butyric acid. Butyrum, you might have heard the term butyrum. It's a Latin word used for butter. Butter. And this is the acid present in butter in the form of its ester. Butter. Okay. Hence the name butyric acid. And in this case, it's there will be a prefix corresponding to this branch. In this case, you have to number from the functional group through the longest carbon chain. If you number this way or in this way, both are same. Okay. So you number from this end 1, 2, 3. So this CS3 is considered to be the substituent. Is indicated by prefix and with the position. This methyl group is attached to second position. So 2-methyl propanoic acid. 2-methyl propanoic acid. There is a break. Actually, it's a mistake. IUPAC names are written without any break. You know the rules. Two numbers are separated by commas, and the number and letter is separated by hyphen. Okay, and there should not be any break between two words, two letters. So it should be given continuously. Ethanoic acid. But break പാടില്ല എന്ന് പറഞ്ഞ തീരനുസരിച്ച് ഇനി നമുക്ക് മനസ്സിലാവുന്നത് അങ്ങനെ ഇടുന്നു മാത്രം നമ്മൾ എഴുതുന്നു ഇച്ചിരി അത് കറക്റ്റ് അല്ല. Okay, now you know the nomenclature. Whatever may be the compound, organic compound, especially carboxylic acid, that will be given. If you are asked to write the IUPAC's name, definitely all of you can. Okay, I expect so. Nomenclature of other acids. See this one. You number from this end. 1, 2, 3, 4. And in the third position there is an unsaturation. Word root will be BUT. Am I right? But plus primary suffix ene since there is double bond. But plus ene plus secondary suffix oic acid. 3-butanoic acid. On combining word root, primary suffix corresponding to this double bond and secondary suffix corresponding to this functional group, you will get 3-butanoic acid. And in case this double bond may be cis or trans, in that case the term cis or trans may be given as the prefix. Okay, according to IUPAC, recently the terms Z and E are usually used. Z is usually used for cis and E is used for trans. You know the concepts. Anyway, I am not going for much details. See, this one is trans 2-butanoic acid. How many carbon atoms are there? 1, 2, 3, 4. You number from this end 1, 2, 3, 4. In the second position there is a double bond. 2-butene. And this configuration, geometrical configuration is trans. It is given trans 2-butanoic acid. And you compare this one. This one is aromatic acid that we have already seen. This one is benzoic acid. Benzene plus 1 oic acid. It is reduced to benzoic acid. It is accepted. Widely accepted. Actually, benzoic acid is a trivial term, but it is accepted in the IUPAC also. And you consider this one. In this case, this one is considered to be the parent chain and this phenyl group is considered to be the substituent. So you number from this end 1, 2. Okay. In the second position, there is a phenyl substituent. Hence the name 2-phenyl ethanoic acid. Why it is ethanoic acid? There are only two carbon atoms are there in the parent chain. So word root will be ETH. Since it is saturated, this is aromatic chain is not considered as unsaturated. Okay, it is stable. It is as stable as a saturated compound is. Hence, it is shown in this way: 2-phenyl ethanoic acid. It's a saturated acid. And you go for this compound. In this case, you number from this end: 1, 2, 3. Word root will be prop. Primary suffix will be ENE. Then in the second position, there is a double bond. In the third position, there is a phenyl group. And the position of the double bond may not be significant because in the first position we cannot have such a double bond. Okay. Hence, in the third position, this substituent is given. So the name is 3-phenyl pentenoic acid. Sorry, actually I have mistaken. 3-phenyl propanoic acid. Propanoic acid. Spell check error എനിക്ക് തോന്നുന്നു. 3-phenyl correct ചെയ്യണം. 3-phenyl propanoic acid. And this one is, see, oxalic acid ആണ് ഈ സാധനം. COH dicarboxylic acid എന്ന് പറയുന്നു. ഒരു നമ്പർ ഇങ്ങനെ കൊടുക്കും, ഇവിടെ നമ്പർ ചെയ്യും, ഇവിടെ നമ്പർ ചെയ്യും. 1, 2. This is a carboxylic acid containing 2 carboxylic acid groups, and these carboxylic acid groups are present in 1, 2 positions. Ethane dioic acid. What to say? Positions may be given, may also be given. See, ethane 1,2 dioic acid. So 1,2 can be neglected by since there are 2 carbon atoms and 2 carboxylic acid, we cannot have 2 carboxylic acid groups at the first position. So this will be sufficient, ethane dioic acid. Have got the idea? Similarly, all organic compounds can be named according to IUPAC. And actually, in this case, IUPAC will be somewhat easier since it is a common way. Then, structure of carboxylic acid. Resonance plays an important role in carboxylic acid and carboxylate anion. See in the figure, the structure of a carboxylic acid is given: RC double bond to OH. In the oxygen, there are 2 lone pairs also. See, so there will be the formation, the phenomenon of resonance. See, resonance starts from, electron shift starts from here. This bond shifts to form a double bond. So, in order to remain the tetravalency, this bond will be shifted towards this oxygen. So, it will be a negative charge. This will be the structure, resulting structure. This oxygen will be positive, and this oxygen will be negative. And the resultant structure, these are the 2 resonance structures. You know what is meant by resonance. Resonance is indicated by double-headed arrow. This one is the typical representation for resonance. 2 resonance structures are there, and the actual structure will be the composite of these 2 structures, structure A and structure B, and this composite is represented in this way. RC is a bond between carbon and oxygen. Here also carbon and oxygen, and these 2 oxygens are same. These 2 oxygens are identical in this case. See, in the first stage, bond will be between this carbon and oxygen, and in the second structure, the double bond will be between these 2. So the hydrogen may shift towards this this oxygen or this oxygen. Got the idea? So we can write the resonance hybrid in this way: RC single bond O, single bond O. A partial bond, this represents a delocalization. And as a whole, this will get a negative charge, and in order to balance this negative charge, H plus ion will be there. This is the H plus ion. This is a hybrid. And regarding the orbital diagram, orbital diagram is somewhat related to MO theory. According to MO theory, this is the orbital of carbon, this is the orbital of p orbital of oxygen and p orbital of oxygen. And this 1 unit charge, 1 electron will be circulating in this way. Delocalization. Delocalization starts from here, this here, and this electron cloud forms two streams, one above the plane and one below the plane. You got the idea? The electronic delocalization. This electronic delocalization is nothing but the resonance. The stability of carboxylic acid is due to this resonance operation. Okay. Anyway, you may be asked to write why carboxylic acids are stable, or why they exhibit acidity. That we will see later. And see, carboxylate anion is also a resonance hybrid. See, this is a carboxylate anion after removal of this OH. Why this OH group undergo dissociation? Oxygen is electronegative, whereas this hydrogen, the previous structure, that will be better. See, oxygen will be electronegative, hydrogen will be electropositive. So, the electrons present in this covalent bond between oxygen and hydrogen will be more shifted towards this oxygen, because oxygen has got higher electronegativity. Okay, got the idea? So, this bond will be somewhat shifted towards the oxygen, that makes this bond somewhat weaker. So, in presence of any reagent, this oxygen hydrogen bond undergo cleavage, breakage very easily. And after removing this hydrogen, it forms RC double bond O minus. This is a carboxylate anion. This carboxylate anion, this free negative charge shifts towards this, and this bond towards this oxygen in order to conserve the tetravalency of carbon. The remaining structure will be, the resultant structure will be this one. This is structure A, structure B. And see, these two structures are identical. Why? See, this structure, if rotated through a C2 axis, along this axis, you will get this structure. C2 axis, correct line. These two structures are identical. And regarding resonance, you might have studied the fact that if the structures, canonical structures or contributed structures or resonance structures are identical, stability will be much high. Okay, you may be remembering the fact. And in this case, see, unlike in the case of resonance structures of carboxylic acid, in the case of carboxylate anion, the two structures are similar or identical, and stability will be more and resonance energy will be more. Higher the resonance energy, higher the stability. Good idea. So, carboxylate anion is more stable. Since I can explain this way. Since the two structures are identical, in this case, resonance energy is higher compared to corresponding carboxylic acid. Hence, stability of the carboxylate anion is greater. And the resonance hybrid, in this case, that can be written in this way, represented in this way. There is a negative charge. See, orbital diagram corresponding to this one is, see, so carboxylate anion, and negative charge is delocalizing above the plane as well as below the plane. So, pi electron cloud, delocalization. It's nothing but MO concept. So, whenever you compare carboxylic acid or the corresponding carboxylate anion in this given acid, which one will be more stable? Carboxylate anion will be more stable. Okay, good idea. Then acidity of carboxylic acid. Carboxylic acid exists in a dynamic equilibrium in which the equilibrium is more shifted towards the right. See, this is a carboxylic acid. When put in water, it remains in an equilibrium with the ionized molecule, carboxylate anion and H3O+. Good idea? By this reaction, according to Arrhenius theory, see what you see, observe through this reaction. By this reaction, this compound can release H plus ion in solution in water according to Arrhenius theory. Hence it is an acid. Okay, why carboxylic acid is acidic? The fundamental explanation is, according to Arrhenius theory, any substance that liberate H plus ion in solution, not in solution, in water, solution or in water, that is an acid. See, in this regard, this carboxylic acid is an acid. Okay. Secondly, see, we have seen the two resonance structures corresponding to the carboxylic acid as well as the carboxylate anion. This OH group is somewhat labile. Why it is so? I have already told you in the previous slide. See, oxygen, this OH bond is, according to covalent concept, is a perfect covalent bond. If it is a perfect covalent bond, the electron pair between oxygen and hydrogen would have been shared equally between oxygen and hydrogen. Am I right? But actually it is not so. So polarity develops. Why polarity develops? Since oxygen is more electronegative compared to hydrogen, the shared pair will be more shifted towards this oxygen. So that weakens this OH bond, and in presence of an attaching reagent, OH bond undergo breakage, liberating H plus ion and carboxylate anion. Okay, that's the first reason. That is a basic principle behind acidity of carboxylic acid. And thirdly, see, once this carboxylate anion is produced from this carboxylic acid, it is more stable. See, this is the reaction, formation of carboxylate anion. This reaction is, this compound is more stable. Not compound, this ion. This species more stable. Then equilibrium will be more shifted towards right. And I shall represent in this way, a longer arrow towards right and a shorter arrow towards left. Equilibrium will be more shifted towards the right. So in the equilibrium, unionized, compared to unionized molecules, ionized molecules will be higher in the equilibrium with the liberation of H plus ion. That shows acidity. Suppose you may be asked to write the reason why carboxylic acid exhibits acidity. How can you explain? Your explanation should include three facts. First one is Arrhenius theory. What is an acid? Okay, I have already told you. Secondly, OH bond is weaker, hence it can undergo breakage in presence of an attacking reagent, especially a base. Why? I have already given you the reason. Then thirdly, once carboxylate anion is formed, even though the reaction is reversible, equilibrium will be more shifted towards right. Hence, carboxylic acid has a tendency to remain in the carboxylate anion form. That tendency is greater. With these 3 points, you can illustrate acidity of carboxylic acid. This reaction forms the basis of acidity of carboxylic acid. The equilibrium constant, whenever you write the equilibrium constant for this reaction, you will get in this way: K is equal to concentration of RCOO minus into concentration of H3O plus, all divided by concentration of RCOOH, that is the unionized acid. Okay, and the term corresponding to H2O, concentration of H2O, is absent here. You know the reason. Concentration of H2O is taken to be constant in presence of large H's of water, and it is cross multiplied, then K is written as Ka. So K is equal to this expression. And see, in order to compare the acidities of carboxylic acid, usually we use the term pKa. P stands for a mathematical operator which is equal to negative common logarithm. pKa stands for negative common logarithm of Ka, just like pH. That is equal to negative logarithm of the whole expression. And strength of organic acid is compared in terms of their pKa values. Let me explain one more thing. Higher the acidity of the carboxylic acid, higher the value of Ka, lower the value of pKa. Got the idea? Lower pKa value represents a highly reactive acid, whereas high value of pKa represents a weaker acid. Okay. Why it is so? This is negative common logarithm. Negative common logarithm. It's an inverse relation. Hence, so. Okay, let me stop here. Let me stop here. Time being, you study well. Tomorrow we shall see the rest of things. Okay. Okay. Thank you. Thank you once again.